Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are in lecture number 2 for third week of wireless and mobile communication. Actually this lecture is in continuation to our last lecture, that is lecture 1 of this week. In our first lecture of this week we started discussion on interference and how does this interference affect the capacity of the system. So we continue our discussion from the previous lecture. In our previous lecture we discussed that there are two important types of interferences in cellular system, which are co-channel interference and adjacent channel interference. And in our last lecture we started discussion on co-channel interference. So before proceeding further, let me quickly review what we have discussed so far in regard to co-channel interference. What is co-channel interference? Co-channel interference is actually interference coming from a co-channel in a cellular system, that is the channel which is using the same frequency as the one under study. In order to analyze the effect of interference, the most important parameter is signal to interference ratio, that is SIR. In calculating the effect of interference, another important parameter that we use is co-channel reuse ratio, which is denoted by Q. This co-channel reuse ratio is defined as the D upon R, where D is the distance between base stations of two co-channels and R is the ratio, R is the radius of the cell. This co-channel reuse ratio is related to the cluster size by this relationship, that is under root 3n. So if we know the cluster size, we can use that cluster size to calculate the co-channel reuse ratio. Second thing that we discussed in our last lecture was the received power at a specific distance. If we know the distance from the reference point D naught, we know the distance from the base station, and we can calculate the received power at that distance by using this relationship, where D naught is the reference distance and P naught is the power at the reference distance, and N is the path loss index that is based on the wireless propagation environment. As we said that the important parameter for analysis of interference is signal to interference ratio. So the co-channel SIR is denoted by this expression, where S is the power from the serving base station, and this denominator is actually sum of all powers which are coming from the co-channel interferers. By using the relationship of power with distance, we can transform this expression into this form, S over I, where numerator is distance of mobile equipment from the serving tower raised to power minus n, and at the denominator we are using the sum of distances from all the interferers. This is the generalized expression and can be used to calculate signal to interference ratio at any point or any system or for any mobile equipment. However, in order to make some useful conclusions from this expression, we want to slightly simplify this expression by making some assumptions. So let us try to simplify this expression. Of course, this assumption would represent an approximate value, but they are good for understanding purposes, and if one needs to calculate an exact value, he or she may be referred to this expression, which is a generalized expression to calculate the signal to interference ratio. So the assumption that we are discussing, first assumption is that we will be focusing on interference which is coming from the first tier of co-channel cells, because first tier of co-channel cells, they are at close distances, and all the higher tiers, they are relatively larger distances and eventually contribute less towards interference. So we are ignoring the interference which are coming from second and tier and onwards, and we will be calculating the interference with for the first tier co-channel cells. Second thing regarding the interference is that because we are trying to calculate the interference at the mobile equipment, so the most important case for the interference will be the one where the mobile equipment is placed at the farthest distance from the serving base station. So when the mobile equipment is close to serving base station, eventually it will be receiving significant amount of power from the serving base station, and the effect of interference will not be significant. So the worst case interference occurs when the mobile is farthest away from the serving base station. Farthest away means the mobile equipment is at the edge of the cell. If it's circular cell, of course all the distances are equal, but since we are using a hexagonal geometry, so the most farthest point from the base station will be treated as any of the vertices of that hexagonal. So if we want to calculate the significant or worst case effect of interference, in that case we have to place the mobile equipment at the vertex of hexagon. In this case, the distance of mobile from the serving tower would become equal to the radius r. So the numerator, which is giving you the distance of mobile from serving tower, that becomes equal to r. Second thing is regarding the denominator, which is distance of the mobile from the ith interferer. Although this distance depends on the location of mobile, because if we change the location of mobile, of course that distance would change, but on an average the distance would remain same for all co-channel interferers. So we can if for simplicity, for simplifying our calculation, we can assume that all the distances from the ith interference, they are exactly the same and they are equal to d. So d is actually representing the approximate value for the distance from the mobile equipment, but you must note that by our definition we have denoted d to be the distance from the base station, not from the mobile equipment. But for the for simplifying this expression, we are assuming d to be equal to the distance from mobile equipment to be equal to d. This is not true in the sense that this differs from the actual distance, but on an average the effect would not be significant. Why the effect is not significant? Because if the distance is decreased for one of the co-channels, that is mobile is moving towards a co-channel, then that means it will be moving away from other co-channels. So if one of the distance is increased, the other will be decreased. So eventually on an average you will be getting the almost same effect again. So this expression would give you an approximate value only. So I can replace this distance from ith interferer with d here. So I replace it with d, and since all the distances are taken to be same, so the overall summation would be equal to this d raised to r minus n multiplied by I0, where I0 shows the number of interferer which are significant. So this is 1 upon I0 d over r. I have switched the numerator and denominator to make the index positive. So signal to interference ratio is dependent on path loss index as well as this d upon r ratio, which is a co-channel reuse ratio. or so we can relate this SIR with the cluster size and co-channel reuse ratio, because this one is actually the co-channel reuse ratio Q, and Q is equal to, for hexagonal geometry, is equal to 3 upon n. So we can simplify this signal to interference ratio to give expression like this. You can see that this expression relates the SIR to the cluster size n, and we have discussed in our last week's lectures that this cluster size n determines the overall system capacity. We discussed this expression C is equal to mkn. Therefore, we need to set a proper value of n so that we get a minimum acceptable value for the SIR as well as maximum possible value of the capacity. But you should note that this expression is based on certain assumption, so this will give an optimistic result in many cases, but these results would be sufficient enough for some generalized analysis. However, for exact results we need to refer to the geometry and calculate the exact distances between different mobile equipments and different co-channel interferers. So let us take a simple example here. We assume that there are 6 closed cells, that means the reuse ratio the cluster size that we are using is 7. So we have 6 closed cells close enough to create a significant interference, that they are approximately at equal distances from the desired base station. So we are referring to this assumption that we have done to derive this expression I is equal to I naught d. So I0 is actually 6 because we have 6 co-channel cells interferers which are significant enough to produce significant amount of interference. The old US AM system, it required signal to interference ratio to be at least 18 dB. So we want to know how much the signal, the cluster size is required to have this signal to interference ratio 18. So let us assume that the path loss exponent n is equal to 4. In that case, we can write SIR to be, we want SIR to be greater than 18 dB. In fractional value, this S by I should be 10 raised to power 18 over 10, which is actually 63.1. So we want signal to interference ratio to be greater than 63.1. As signal to interference ratio is related to this cluster size by this expression, so I can replace it by under root 3 n raised to power n upon I0. And as small n, the path loss index is assumed to be 4. In that case, we can write this expression to be 9 n square upon 6, where I0 is equal to 6. Therefore, n square comes out to be 42, and we should have n is greater than 6.5. So having greater than n greater than 6.5 means that the minimum cluster size that we should use is 7. So this, having the 7 cluster size, would give you signal to interference ratio of 18 dB or higher, which is required to establish a reasonable communication in old AMPS mobile systems. While we have given an expression here n greater than n greater than 6.5, you should note that this n can only take specific values. For this particular case, we have taken 7, which is a valid cluster size, but in certain case, if n comes out to be 8, we cannot choose n is equal to 8, because the higher cluster size for n, if we are not taking 7, it should be 12. Okay, let us take another example. So let us assume that we have a 7 cell cluster, and a mobile unit is at the boundary of one of the cells. So you can see we have a center cell and a mobile equipment is placed at point A at the boundary of cell and is experiencing interference from 6 co-channels in the first year as illustrated. So these are only the interfering first year co-channels. All other channels are not shown in this figure. Assume that path loss exponent is 4. So path loss, the environment we are assuming is relevant to path loss exponent of 4. So we want to calculate the signal to interference ratio in terms of co-channel reuse ratio. So we want to calculate S by I. Okay. In order to do that, first thing is we need to calculate this distance R, because what we need is the distance from the serving base station and divide by sum of all the distances which are from the all possible interferers. But here from the base station, which will be at the center of this cluster, is center of the cell, so eventually the distance to mobile A would be R, which is radius of cell. For all others, we can approximate the distance. For example, if we are taking this one, this cell A, the distance from this one up to this center of base station is D, and from D to this boundary is R. So basically you can see, let me show with a pointer. So distance from here to here is D, and so this distance is D, and from here to here is R, and this distance, this direct distance, would be different. You can use a trigonometric relationship to calculate this distance, but if you think of the cluster geometry, you will see that this D is actually much greater than R. In that case, this effect of D will be dominant and effect of R will be smaller. So therefore we will therefore we can conveniently make an approximation that this direct distance is equal to D over R. Similarly, for this point we can make an approximation that distance is equal to D plus R. These are approximations. Similarly, this one can be approximated to D, this one can be approximated to T, and the two near one, they can be approximated at D minus R. So for this geometry, we can assume that two of the co-channel base stations, they are at a distance of D plus R. Two of the base stations, they are at a distance of D, and two of the base stations are at the distance of D minus R with some approximation. So by using our relationship, this is our relationship. So numerator will be equal to R, and denominator is actually comprised of 6 terms. 2 has distance of D plus R, 2 has distance of D minus R, and one is and other 2 has distance of D. And if we divide numerator and denominator by R, we can write it as because these two are same, so I have replaced it by 2 times. Everything is 2 times here, so we can write it as D over R plus 1 and D over R plus 1 and so on. So this D over R is defined as the co-channel reuse ratio. So this can be written as in terms of Q. So S by I for this expression is approximated as 2Q plus 1 raised to power minus 4 plus 2Q minus 1 raised to power minus 4 and 2Q raised to power minus 4. And you can see that for n is equal to 7, the co-channel reuse ratio is 4.6 that we had discussed in our last lecture as well. Therefore, the worst case signal to interference ratio is approximated as 49.56, which is actually 17 dB. So what do you suggest? Should we use n is equal to 7 or not? Our requirement was to have signal to interference ratio above 18 dB, but for n is equal to 7, this worst case signal to noise ratio comes out to be 17 dB. 17 dB is slightly different than 18 dB signal to noise ratio. If we want to improve this signal to interference ratio, we need to go for higher cluster size, which is 12, which corresponds to I is equal to J is equal to 2. So basically, if you strictly want to meet the requirement of 18 dB, in that case the cluster size should be 12. Of course, having 12 cluster size would reduce the capacity by this factor of 7 by 12. So we have a capacity reduction by 7 by 12 because we will be having 1 by 12 reuse ratio as compared to 1 by 7. So these are significant change in the capacity. Practically, because this 17 dB refers to the worst case condition where the mobile is at the corner. In most cases, the mobile would be at somewhere inside this cell, and probability of having mobile will be lesser than what you have at the inside. So in practical cases, if you want to increase the capacity, sometimes you settle on 17 dB signal to interference ratio, but in that case any mobile which is at the vertex would be suffering from higher interference, but overall system would have significantly improved capacity because of the 7 cell reuse. So this brings us to the conclusion of the discussion on the co-channel interference. Let me quickly summarize some of the important points that we have discussed with respect to the co-channel interference. First of all, the radius of the cell has no effect on the signal to interference ratio, because if we increase the radius, we have to increase the distance as well, and the ratio becomes same. Secondly, the path loss exponent has significant effect. If we have higher value of path loss exponent n, that means the signal to interference, it will significantly affect the signal to interference ratio. You can see it from here, this expression here, that having higher value of signal to interference ratio would significantly affect higher value of n would significantly affect the signal to interference ratio. So having higher value of n would give you higher value of signal to interference ratio. That means having higher value of n is good from the interference point of view, because it gives you higher value of signal to interference ratio, although it gives you higher losses. But higher path loss in the urban environment is beneficial from the interference point of view. To get an acceptable value of SIR around 18 dB or so, we need a cluster size of at least 7 with path loss of around 4. So this concludes the discussion on the co-channel interference. Let us move our discussion on to the adjacent channel interference. So first thing, what is adjacent channel interference? Adjacent channel interference results from the interference coming from any adjacent frequency band which is allocated in the same cell. Generally, each cell is allocated multiple frequency channels, and in order to extract one of the channel for communication purposes, we generally use filtering. But the important thing is that the filtering is non-ideal process. Generally, the ideal filter that we study in theoretical aspect, from theoretical aspects, the practical filters, they differ from that ideal response, and eventually that ideal response, that non-ideal response results in some interference or some of the frequencies being extracted by the filter which are not intended to be there. So some of the stop band frequencies, they leak into the pass band. and eventually this causes the adjacent channel interference. Generally, this adjacent channel interference is a reverse channel effect. Generally, this is affected on the reverse direction. That is, when a mobile is trying to communicate with the base station. So this interference effect is dominant at the base station side. So the question is how the real filter differ from the ideal response. Let me show you a simple diagram. This is the response of ideal filter. On the left side, you have a stop band, a pass band, and another stop band. So what we expect that at the stop band all the frequencies are suppressed, at the pass band all the frequencies they are passed, and at the stop band all the frequencies are suppressed. But the real filter, they do not have response like this. The real filter, they have a pass band, but the response is not constant. It starts changing, decreasing in the pass band. So there is certain variation here. Secondly, at the stop band, frequencies are not exactly zero. They are reduced to certain level, maybe 20 dB or 30 dB. As you go further from this edge, the reduction is higher, but this is not exactly zero. Third thing, in between the pass band and the stop band, there is a transition band where the response is gradually changing from this 3 dB point to whatever desired value we have. So that means this transition and non-zero stop band, they are actually responsible for causing the adjacent channel interference. Let us take two simple scenarios how the interference occurs. In first scenario, I'll be assuming all the mobile phones, they are approximately at an equal distance from the base station, and for some second scenario, we'll assume some mobiles to be close to base station and some mobiles will be far away from the distance. For illustration, we are representing 10 mobiles. So let us start discussion on the scenario number 1. So we are assuming that we have 10 mobiles which are actually almost close at almost same distance from the base station. Since all mobile phones, they are at the same distance, the power which is received at the base station from each of the mobile phones will be approximately equal. So if we try to plot the spectrum of the power received at the base station, it would look somewhat like this. So mobile number 1 will the power received from mobile 1 will be this one, and mobile 2 will be having same power, and from mobile 3 will be having same power, and almost same power for all the mobiles. So if we are interested in extracting the signal from, say for example, mobile number 5, in that case we need to use a band pass filter. So we can have a band pass filter, and we set the band pass filter in such a way that the mobile 5, whatever frequency mobile 5 is allocated, it is passed through that band pass filter, and all other frequencies, they are suppressed by around, say for example, 20 dB or higher. So in that case, if you pass the signal from the mobile, all the signals from this particular type of band pass filter, which is centered on the frequency of mobile number 5, so all the signals coming from all other mobiles, they will be suppressed by 20 dBs, like shown in the second diagram here. But the mobile number 5 frequency, it will pass through this band pass filter without any degradation in that power. So eventually the overall spectrum would look somewhat like this, where you have significant amount of power at mobile number 5, but all other powers are reduced to significantly low level, and eventually they will not cause any significant interference, although this small power would even have certain interference effect. But so far we assume that this 20 dB is sufficiently low that it does not have significant effect. So if we have this scenario number 1, where all the mobiles, they are almost same distance, eventually it's very easy to extract the signals which are which we want to extract, which are coming from a specific mobile. and we can use a specific band pass filter to extract that particular signal. The scenario becomes more complicated and more practical when the distances are not equal. So to illustrate that thing, what I have done is that we have used a mobile 5 which is at far away from the base station, and all other mobiles, they are close. So signals coming from all these mobiles to the base station would be strong, and the signal which is coming from the mobile number 5 to the base station would be weak. So eventually there will be the received signal at the base station would not be of same strength. This situation is known as near far effect, where we have some mobiles which are near to the base station, and some mobiles they are far away. Eventually the distribution would be very different than what we discussed in the scenario number 1. This near far effect causes a problem in the extraction of the signal, for example like this. So this would be the spectrum that you would expect at the tower, because all mobile number 1 to 10 except 5, they are close. So you will be getting the base station will be getting significantly high amount of power. But since the mobile number 5 is at farther distance, the power received from mobile number 5 will be very low. So let us assume, just as an example, that the power received by all other mobile signals or mobile stations is 60 degree higher than what we receive from mobile number 5. So basically we are interested in extracting the power of mobile number 5, but we end up in a problem that the mobile number 5 signal is very weak as compared to all other signals. If we try to use the same band pass filter that we discussed in our first scenario, like this one, that we want to reduce the signals, all other signals, by 20 dB, and we pass the mobile number 5, even if we pass our signal incoming signals with this band pass filter, we will not be able to extract the signal for mobile 5, because all other powers, they are 60 dB higher. Even if we reduce them by 20 dB, so still these powers will be 40 dB higher than mobile number 5. So eventually mobile number 5 signal would not be extracted, or would have significant amount of interference coming from all other signals. If you want to extract the signal from mobile number 5, what we need to do, we can use the filter again, reduce it by 20 dB, and then again reduce it by 20 dB, and then again reduce it by 20 dB. There is one possibility that we use multiple filters, and if you use multiple filter, eventually that will make overall system complicated, because instead of using one filter, you will be having multiple filters that will cause processing delay as well as overall processing burden on the system, and also increase the complexity of the system. So you can see that whenever we have this near far effect, the problem of adjacent channel interference becomes significant. So what is the solution? The solution lies in the frequency assignment in the signals. For this example, if you see, we have assumed all the adjacent channels. So mobile number 1 is one channel, the next channel is assigned to mobile 2, and next channel is assigned to mobile 3, and so on. So all 10 channels, they are next to each other. But when we are using clustering, so what we can do, we can assign channels in such a way that two adjacent channels, they are not assigned to same cell. For example, if we have a 7 cell cluster size, so we are trying to assign the channels in a cluster of 7 cells. So we can assign them like this. Channel 1 gets the channel number 1, then we do not assign channel 2, 3, 4, 5, 6 onto the same cell. We would assign channel number 8 here. So there will be a gap between 1 and 8. channel 2 will be assigned to some other cell. So cell number 2 will get channel 2, cell number 3 will get channel number 3, cell number 4 will get channel number 4, and so on. So you can see that between two channels there is a gap. So a gap of 6 channel is provided between two consecutive channels. If you have a gap of 6 channel, as I said, from the filtering, even the real filters, they have when we create a gap, this transition goes down, and this effect goes much below the original value. So if we do not have gap and we can has 20 dB stop band value, but if we can produce the gap like this, like with this type of frequency assignment, we can create an attenuation of 70 to 80 dB. 70 to 80 dB is a significant amount of attenuation to extract the original signal from the adjacent channel. So if we distribute the frequency channels in the cells properly, in that case, even if there is near far effect, the adjacent channel interference can be reduced. How can we do that? For example, coming back to the original case, like this, we have the signals coming here. If we pass it through a filter, eventually, if you pass it through a filter which has a 80 dB attenuation, in that case all these frequencies, they will be attenuated by 80 dB, and this mobile 5 it will not be attenuated. So you will have a situation which looks somewhat like this. Originally it was like this. We have created a gap here. Mobile 1 and mobile 2, they have a frequency gap, a band gap, a wide band gap here. Similarly, from mobile 2 and 3, there is a wide band gap, and so on. So once we pass it through 80 dB attenuator filter, so eventually all these frequencies, they will be suppressed, and we will end up with the mobile frequency which is available here. You can see all the frequencies would be suppressed to a significant level, and the original signal that we are interested in is it will have a higher power level as compared to all other signals. So in this way we can easily extract the signal by using even a simple filter, or even a low pass low order filter, and we do not need to use multiple filters for that case. So the summary is, the adjacent channel interference effect will be there, especially whenever there is a near far effect. The adjacent channel interference will be significant, but in order to combat this adjacent channel interference effect, we use a proper frequency allocation. The channels are allocated in such a way that the adjacent channels are not allocated in the same cell. So if a channel is allocated to cell number 1, the second channel would be allocated to other cells, and the next channel will be allocated to other cell, so that two channels in same cell, they are separated by a wide frequency band. So this wide frequency band allow us to use even low order filters to extract the signals with high efficiency. So eventually the overall effect of the adjacent channel get reduced. So this is the solution to the adjacent channel interference, by properly assigning the frequencies to in the cluster environment, and by that we can have get the control over the adjacent channel interference as well. So this concludes our discussion on the adjacent channel interference. The last thing that I want to talk about with the perspective of interference is the power control. A relatively newer approach in reducing interference is the power control. When we have systems with power control, in that case all the mobile equipment, they are not allowed to use same power at every time. Generally what does power control means? If a mobile equipment is closer to the base station, it transmits the signal with smaller amount of power, and the mobile stations which are at the farther distance from the base station, they transmit with a higher power, so that at the receiver side, that is at the base station, the overall received power is almost same. So generally all the power levels of each subscriber, they are controlled by the base station, and the base station ensures that the mobile transmits with the smallest amount of power which is required to maintain a good quality communication, and they are not allowed to transmit signal at higher power. So with this power control, generally all the received signal from all the mobiles in the cell, they are approximately at the same level, and because all the signals they are at the same level, so the signal which is received at the base station, they will appear like the scenario number 1 that we discussed, and which can be easily extracted by filtering. This power control generally reduces the signal to it's a mistake here. This power control increases the reverse channel signal to interference ratio. It reduces the effect of interference and increases the signal to interference ratio in the system. Secondly, because the mobile equipment, they are transmitting at the lower power levels, so their battery will be conserved, and they can use their battery for a longer period of time. So the battery life is prolonged when with power control. So this is another point which can be used to reduce the adjacent channel interference in the system. So far we have discussed the effect of interference, both co-channel interference and the adjacent channel interference. We have discussed their effect and how we can combat those interferences. We have made a discussion on that. With this we conclude our discussion on the interference, and we stop today's lecture here. Thank you all.